Right now, a machine older than most of your parents is running on less power than a refrigerator light bulb. It's flattened cities, started fires that burned for days, a single word sent to it thousands of people a full day just to arrive. For the last several years, it's still the same crack as no human being has ever heard. One so quiet that no person on Earth. This is the real story of Voyager 1, scientists and where it actually stands in 2026 day after day is stranger than anything its own engineers expected. That crack is the San Andreas fault, the one behind every conversation Voyager 1 Californians have about the big one, alongside its giant earthquake everyone knows is coming someday. Plan was modest, nobody can name a date for. Fly to Jupiter, but this year, in 2026, researchers finally caught the San Andreas, quietly into history that wasn't supposed to be able to do this. Nobody involved in the original design expected either machine to still be transmitting. They only caught it because they stopped relying entirely on human eyes, let alone handed a significant part of the job to a machine. The only reason such an ambitious flight path was possible in the first place came down to a rare planetary alignment that occurs roughly once every 175 years. One that placed Jupiter, Saturn, Uranus, and Neptune all on the same side of the sun simultaneously. No cracked plaster. That alignment let engineers design a route where each planet standing directly on top of it, sipping your morning coffee, you would have felt absolutely nothing at all. The Grand Tour. That's not a hypothetical. Voyager 2 actually lifted off first. It's a real, 16 days later, Voyager 1 launched, and researchers are only now getting a genuinely clear sense. Just 13 days after launch, more than 11 million kilometers away, Voyager 1 turned its camera around. To understand why any of this matters, it helps to understand what the San Andreas actually is at a basic level. Our planet picture the outer shell of the Earth not as one continuous solid piece, at that early stage, as a collection of mission was already turning routine technical milestones, each roughly the size of an ocean that forced people to look slowly drifting atop the hot, semi-fluid. By early 1979, where two of these plates meet Jupiter and grind against one another, unlike anything astronomers had imagined from the San Andreas telescope, one of the largest and most consequential examples anywhere on the planet. Brutal radiation roughly 750 a system of moons complex enough to resemble a miniature drive from Los Angeles to the flybys of Jupiter and later Saturn delivered a wave of discoveries that reshaped planetary science almost carrying most of California's coastline, thin rings nobody knew existed, moons grinds sideways past the North American plate, telescope on Earth carries the bulk of the rest of the country. Jupiter's great red these two plates aren't colliding head-on. Backyard telescopes pulling apart from each other either. Was finally sliding past one another laterally to be a storm larger than Earth scrape along each other's sides in extremely slow motion. A centuries-old atmospheric monster still raging on the planet's surface. This is usually the part that genuinely surprises the world entirely. The two plates move past each other at roughly 2 inches per year, about the same rate your fingernails grow, the first time humanity had ever observed active isolation anywhere beyond Earth. Io wasn't a dead, frozen rock that was violently alive, and it remains the most geologically active place known to always slide smoothly past each other in the way. Then there was Europa, average cracked, icy surface hinting at something even stranger of the fault locked together. Voyager's images suggested a vast ocean of liquid water hidden each other and refused to budge, quietly introducing an idea pushing regard drives planetary completely indifferent to whether the surface one of the best places to search for life. Pressure builds the way tension builds in a frozen moon circling a much bigger world. Quietly, after Jupiter, Voyager 1 used gravity itself how much slingshot is accelerating towards Saturn and arriving in 1980 to hold more momentum. When a stretch of fault stays locked for a full century, Saturn, long imagined as elegant and simple with its single visible ring, turned out to be far more complicated than anyone expected. Coiled like a spring, what looked from Earth like one thin ring exploded on closer inspection into hundreds, when it eventually does let go. Narrow, layered ring structures, the ground on one constantly shifting rather than sideways by 10 feet or more. But the most consequential decision of the entire street came farther than a person, where engineers chose to fly Voyager 1 close past Titan. The historical record backs up just how dangerous that mysterious atmosphere. That decision came with a permanent cost. The northern San Andreas Saturn's gravity bent Voyager 1's path sharply out of the flat plane, where devastating San Francisco within seconds it could never visit another planet. The fires that followed, ignited by broken gas lines, Voyager 1 stoves and made far worse by shattered water mains that left firefighters largely helpless, accelerating into the fastest spacecraft humanity had ever built, heading on a one-way path toward the outer edge of the sun's territory. In exchange, the city's mission got something remarkable. Homes in the span Voyager spinning on chrome arcs. Further south, in 1857, Voyager 1 couldn't actually see Titan's surface directly, since its thick atmosphere was nearly opaque to visible light. But by analyzing what that atmosphere was made of, scientists uncovered something genuinely striking from the air today. Titan is cold enough that methane behaves there the way water behaves on Earth. Comparatively few people lived in that region at the time, and a gas limited casualties. That single discovery opened the door to the idea of lakes occurring today, on a world far in the middle of a region now home to millions of residents. Think about countless freeways, habitability, dense clusters of skyscrapers. Would almost certainly rank among the worst disasters in American history. Engineers back on Earth made a decision purely historical trivia at all. Distant, attached to the side of each Voyager spacecraft spacecraft. In 1989, during the World Series, the size of one of the most watched live broadcasts of the year, snapshot of the San Andreas moved again, recorded in television screens across the country, sounds like briefly thunder, static, wind, and whale song. As a double-decker freeway in the Bay Area is encoded as data showing land crashing down onto everyday human life, while a section of a major bridge broke loose cultures and centuries. 63 people died, championed by a small real-time by a nationwide audience that had tuned in expecting baseball. Was almost absurdly optimistic. That event, for a mission as devastating as it was, wasn't remotely close to the fault's this record might one day drift close enough to another civilization sometimes found and understood, clearing its throat rather than delivering its full voice, sending it represented stretch of the fault doing on its the same segment that ruptured back. The disc has ridden along the entire way, an artifact nobody expected to still matter 50 years later now without a major release. It's tempting to read that extended quiet as reassuring, but after years of quiet travel through tends to mean precisely the opposite. Voyager 1 finally doesn't forgive accumulated pressure simply because it hasn't released. On August 25th, 2012, its instruments picked up something particular segment has been quietly storing it for well over a century and a half. From the sun paired at the same exactly why seismologists spike seriously about particles, the big one arriving from deep in the galaxy folklore. This wasn't a slow fade. Odds of a strong and abrupt earthquake striking the spacecraft had physically struck an invisible wall. 3 and 4 over the next Voyager 1 had crossed the San Andreas, sitting boundary where the solar wind finally runs out of strength. Detailed modeling of a major rupture along that scientists had long assumed this region would behave like a genuinely grim picture gradient, with projections in a range of 1,800 deaths, tens of thousands of additional injuries, the data and damage totaling different hundreds of billions of dollars. The sun's protective bubble, called the heliosphere, driven by ended sharply, forming a real, measurable membrane of plasma from the sun collided directly with plasma. For a long time, that basic lock and release cycle was thought to represent essentially the entire behavioral repertoire of a fault like this one. Sections lock, pressure accumulates steadily and invisibly, and eventually the whole system releases catastrophically in one violent event lasting mere seconds. Push, hold, snap, in that order, over and over across generations. But researchers had long suspected there might be a second, considerably quieter way for a fault to move, one that released a portion of accumulated stress gradually, spread out over hours or even days, without generating any shaking at all. Scientists refer to this as a slow slip event, sometimes described more evocatively as a silent earthquake. On first hearing, the phrase sounds almost self-contradictory. An earthquake that produces no shaking whatsoever seems like a logical impossibility, roughly equivalent to a thunderstorm with no thunder. But the underlying mechanism actually makes intuitive sense once you picture it concretely. Shove a heavy couch across a hardwood floor all at once, and it jerks forward with a loud, sudden screech. Lean into that same couch instead with slow, patient, steady pressure, and it can travel the exact same distance almost silently, sliding smoothly rather than jerking. The San Andreas, it turns out, is capable of that same quiet sliding motion under the right conditions. The persistent challenge has always been detection, since standard seismometers, the instruments most people picture when they think of earthquake monitoring, are specifically built to register shaking, and a genuine slow slip event produces essentially none of it by definition. Catching something that generates no vibration at all required a fundamentally different kind of instrument. The tool researchers eventually built for exactly this purpose is called a borehole strain meter, a remarkably sensitive device installed hundreds of meters underground, engineered not to listen for shaking at all, but instead to detect extraordinarily small amounts of squeezing and stretching occurring in the surrounding rock. These instruments are sensitive enough to register the faint gravitational tug of ocean tides from many miles inland, essentially feeling the weight of incoming seawater pulling gently on the land itself. A cluster of these strain meters has operated continuously for decades at Parkfield, a small, sparsely populated stretch of central California ranch land that happens to sit directly atop a so-called creeping segment of the fault, one that tends to move in frequent small increments rather than locking up for a century at a stretch. That particular characteristic made Parkfield an ideal natural laboratory for studying exactly this kind of quiet, incremental fault behavior, and it's been one of the most densely instrumented, most intensively monitored fault segments anywhere on the planet for years, specifically for that reason. Having all that raw sensor data sitting in an archive, though, was never the same thing as being able to actually read it accurately. Strain meter readings are notoriously messy in practice, full of noise generated by shifting weather patterns, tidal cycles, rainfall soaking into the ground, and any number of other small disturbances that can easily bury a genuine slow slip signal underneath layers of unrelated static. For years, human researchers working through this data by hand could reliably identify only the largest, most obvious slow slip events, while smaller, subtler ones simply slipped past unnoticed, hidden inside the surrounding noise no matter how carefully anyone looked. That situation changed with a study published in the journal Nature Communications in June 2026, led by Dr. Zarazali of the GFZ Helmholtz Center for Geosciences. working in collaboration with researchers from EarthScope and Stanford University, including Professor Gregory Barroza. The team applied a deep learning model, an autoencoder-based neural network specifically designed to learn compact patterns within noisy data, to roughly 8 years of continuous strain meter readings collected at Parkfield between 2009 and 2016. The system was trained specifically to recognize the faint, slow, smooth rise and fall signature characteristic of a genuine slow slip event, while learning to filter out the tidal fluctuations, weather-related noise, and other confounding signals that had defeated purely manual analysis for years. The result was the first genuinely comprehensive catalog of short-duration slow slip events at Parkfield ever built directly from continuous strain observations, and the scale of what it turned up was striking. The system identified 92 separate slow slip events in total, of which 21 had never once been detected across years of prior careful manual review of that exact same underlying dataset. 14 of these newly identified events were further confirmed independently by nearby creep meters, a completely separate class of monitoring instrument measuring ground deformation in a different way entirely, which is precisely how the research team was able to rule out the possibility that the neural network was simply hallucinating patterns that weren't genuinely present in the underlying physical data. What makes this finding significant extends well beyond the detection method itself, impressive as that method is. It comes down to what the researchers found when they compared the precise timing of these slow slip events against other seismic activity occurring in the surrounding area. Low-frequency earthquakes, an unusually weak, deep class of seismic signal specifically associated with fault slip processes, consistently increased in frequency following a slow slip event. In other words, these silent, imperceptible movements don't appear to be happening in complete isolation from everything else going on within the fault system. They appear instead to nudge the surrounding rock in some measurable way, subtly shifting accumulated stress onto adjacent sections of the fault nearby. That's precisely the detail that's made seismologists sit up and take genuine notice, because it raises an obvious and fairly urgent follow-up question. Could a slow slip event occurring on a creeping section like Parkfield ever transfer enough incremental stress to meaningfully nudge an adjacent, fully locked section, one already carrying more than a century's worth of accumulated pressure, measurably closer to eventual failure? Nobody currently has a confirmed, definitive answer to that specific question, and the researchers involved have been notably explicit and careful that this discovery does not constitute evidence of any imminent large earthquake. Slow slip events have almost certainly been occurring on this fault system for as long as the fault itself has existed in its current form. And genuinely, major ruptures remain comparatively rare events by any reasonable measure, which strongly suggests that the overwhelming majority of individual slow slips likely occur without ever triggering anything dramatic downstream. What this particular study does firmly establish, though, is that the older, simplified mental picture of a fault behaving as either fully locked and silent or catastrophically rupturing was meaningfully incomplete all along. There's an entire intermediate category of quiet, ongoing fault activity that had gone largely unrecorded and unrecognized, hiding in plain sight inside decades of collected but underanalyzed data. Researchers, including University of Washington seismologist Harold Tobin, have publicly noted that these findings raise genuinely fresh, open questions about exactly how stress transfers back and forth between creeping and locked sections of the broader San Andreas system, questions that now need to be systematically checked against other stretches of the fault to determine whether comparable hidden slow slip activity might be occurring in other locations that simply haven't been studied with this same level of instrumental density and analytical sophistication yet. It's worth being genuinely clear about what this discovery does not mean, since that clarity matters as much as the discovery itself. It doesn't mean scientists can suddenly predict the exact timing of a major future earthquake. They explicitly still cannot do that, and researchers in this field are consistently the first to say so plainly and without hedging. What it does mean is that researchers now possess a genuinely new, considerably more sensitive way of continuously watching one of the most extensively studied and most objectively dangerous fault systems on the entire planet. And beyond that, a broader research approach, systematically applying machine learning to years of previously underanalyzed strain data that can realistically be pointed at other fault systems and other archived datasets located anywhere in the world. Understanding a natural hazard with greater precision is, generally speaking, how risk management genuinely improves over time, rather than being a reason for public alarm in and of itself. California has spent decades and enormous sums of money making the state materially tougher against exactly this kind of eventual rupture, well before any of this particular AI-driven discovery emerged. Bridges have been systematically reinforced to bend under stress rather than break outright. Hospitals, schools, and older brick buildings that historically crumbled during strong shaking have been retrofitted using hard lessons drawn from past earthquakes. Building codes have been substantially rewritten in response to exactly this kind of accumulated experience. There's now an early warning system covering the entire West Coast that, while it obviously cannot stop an earthquake from happening, can detect that a quake has already begun and issue a warning that travels faster than the resulting shaking itself, giving people anywhere from a few seconds up to roughly a minute of genuine advance notice depending on distance from the epicenter. That narrow window is more useful in practice than it might initially sound. Trains can automatically slow down to avoid derailing. Fire station doors can pop open in advance so they don't jam shut under structural stress. Surgeons in the middle of delicate procedures can pause and hold steady. School children can duck under a desk before a classroom actually starts shaking. All of that existing infrastructure exists precisely because of the same kind of patient, detail-oriented, long-term monitoring work that just uncovered these previously hidden slow-slip events at Parkfield. Step back from the individual technical details for a moment and consider what actually happened here at a broader level, because there's something genuinely notable in it beyond the specific earthquake science. A fault system that has legitimately terrified people for well over a century was, this entire time, quietly doing something in secret, something so gentle and so subtle that not a single human being anywhere could reliably catch it happening in real time. Rather than simply accepting that limitation as permanent, researchers built instruments delicate enough to detect the pull of ocean tides from miles inland, buried those instruments deep underground, specifically to shield them from surface noise, and then trained a machine specifically to listen for whispers that human researchers, no matter how careful or experienced, consistently couldn't hear on their own. This is far from the last word on the subject either. The same core technique, training a neural network to extract faint, previously invisible signals out of years of noisy archived sensor data, isn't remotely limited to this one fault or this one dataset. It can, in principle, be pointed at fault systems anywhere on Earth, and at years of previously collected data that nobody has ever had sufficient time or sufficiently sharp analytical tools to properly examine before now. This isn't a story about an imminent disaster, and it was never framed that way by the researchers who actually did the work. It's a story about scientists finding a genuinely new set of eyes for a fault system that's been quietly keeping secrets for considerably longer than anyone previously realized, and using those new eyes to close a real, meaningful gap in decades of accumulated earthquake science, one hidden slow slip event at a time.